Now we are going to move on to the concept of independence. Okay, so two events A and B are said to be independent if the probability of intersection equals the product of their probabilities. All right, so we have this. If this equation holds, then they are independent. Okay, and by this, consider this the following theorem: if A, B are independent, then we have the following equations. All right, provided the probability of B is greater than 0, right? And this one equals this, provided the probability of A is greater than 0. Okay, so the proof is pretty simple. All right, so let me just prove the first one. Okay, this theorem P of A given B, right? By definition, on the top is their intersection over P of B. Right, so now this one is on the top is considered independent, right? So therefore we have on the top is P of A, P of B over P of B, right? So these two cancel out, so it's P of A, right? So therefore this one, similarly, you can also prove this one, B given A, right? So this one equals, all right, on the top is the intersection, A intersect B, over the bottom is what? P of A, right? Again, they are independent, so A, B over P of A. All right, so this one cancel out, so you have equals P of B. All right, so basically that's what we have, right? So independence, and we have this conditional probability if they're independent. So this tells us the occurrence of B does not affect the probability of A, right? P of A given B is the same as P of A, and P of B given A is the same as P of B, right? So the occurrence of one event does not affect the probability of another event, right? So that's the independent, because they're independent, right? They're independent, okay? So now let's consider this example. Consider rolling a fair die twice. A be the event that first row results in a 4, and B be the event the sum is an odd number. Okay, very interesting, right? So determine whether A and B are independent. Okay, so now for this one, you got to be careful, right? So what is the sample space, right? So twice, right? So a fair die twice. So it's going to be 1, 1, right? And 1, 2, and 1, what? 6, right? So, and then 2, 1, 2, 2, 2, 6, right? And then you have what? 6, 1, 6, 2, and 6, 6. Basically, you have what? This is the sample space, right? So all the possible outcomes. A is the event that the first row is a 4. So what is A? A is basically, the first row is a 4, so that's going to be 4, 1, 4, 2, till 4. Okay, and 6, right? So you have, this is our A, and what is B? B says it's the summation is an odd number. Okay, so then let's say it's gonna be 1, 2. The summation is 3, right? And 1, 4, right? And 1, 6. Now you have 2, 1. Well, that you need to find all these, right? So, and then what? In the end, you have 6, 5, right? 6, 5. So then you need to see, okay, so what is their intersection then, right? A intersect B equals what? C A intersect B. All right, so 4, 1 is good. Right, it's in A, and also there's summation 4, 1, 4, 3, and 4, 5. Okay, so this is the intersection, right? So now you need to know, basically determine whether these two are independent. You need to figure out if the probability of the intersection equals the product of their probabilities, right? So what is the probability of A? Right, it's a fair die, so they're equally likely. So there are 6 outcomes in A. So in total, there are 36. So it's a 6 out of 36, which is 1/6, right? And similarly, you have P of B. Now you need to know how many are there in P of B, right? So there are 3 in each rule. All right, 3 in each rule actually, right? So 1, 2, 1, 4, 1, 6, 2, 1, 2, 3, 2, 5, 3, 2, 3, 4, 3, 6. So 3 in each rule, right? 3 times the 6, that's 18, right? So that's 18. 18 out of 36, that's basically just 1/2, right? So, and also you can see the probability of A intersect B. As we can see, there are 3, right? 3 out of 36, which is 1/12. Okay. Now, do we have this equation to determine whether they're independent? As we have what? The probability of their intersection is, right, P of A times P of B. Right, 1/6 times 1/2, that's 1/12, right? So therefore, what? By definition, A and B are independent, right? So here we go, right? So these two events are independent, right? So now for this one, you got to be careful. Find the sample space, right? And then identify A and B and their intersection. You find the probability of A, find the probability of B, and then find the probability of their intersection, right? And then see if the equation holds. Is P of the intersection equals the product of their probabilities, right? So if the equation holds, they are independent. Otherwise, they are not, right? This is just a bad definition, right? So here you see that this is bad definition, right? So if they are said to be independent, if this equation holds. If this equation holds, they're independent. Otherwise, they're dependent. All right, so otherwise, they are said to be dependent. All right, so dependent. Okay, very good. All right, very good. Let's consider another example here. Okay, so consider this example. 2 computer programs are running simultaneously on 2 different computers. Let A be the event that the first program is successful, and B be the event that the second is successful. Assume A and B are independent with this one, all right, and that one. Find the P of B and find the probability of the union. Okay, so now here, so this condition is this one. So let's see for what do we have from the question, right? So probability of B given A union B. All right, so now this one equals, on the top is the probability of the intersection, B intersect their union, A union B. All right, on the bottom is the probability of A union B. right? So now we can see that on the top is simply what? B is a part of the union, so the intersection is B, a probability of B, right? Now over the bottom is the P of their union, right? The union is P of A plus P of B minus the probability of their intersection. All right. Right. So now, because they're independent, right? So they're independent. So this one can be written as their product. Okay, so this one equals, again, P of B, P of A plus P of B minus their product. Right, equals what? 2/3. Right, this is going to be an equation. All right, so another one is the second, right? So here, in addition, we also have P of A given B is 1/2. Now, however, you see that A and B are independent, right? So therefore, what? This one is actually what? P of A. Yes, because they're independent. P of the conditional probability is P of A. So P of A is 1/2 because they're independent. Okay. Now, therefore, these two equations, right? So can implies what? You can see P of A, plug in P of A in here, so you can solve for P of B, right? So you find a P of A, and you can find P of B, right? So you can just plug in P of A and do this calculation here, right? So that's going to be P of B, okay, over 1/2 plus P of B minus 1/2 P of B, right? So which is P of B over 1/2. Okay, so 1/2 plus 1/2 P of B. All right, so equals what? 2/3. Now this one can be easily, you can easily find P of B, right? So let me just put it on here. P of B equals 3PB, 2PB, PB is 1/2. Yes, PB is 1/2. I believe so, right? PB is 1/2. Okay, so PB is 1/2. So that's going to be our part A. Now you do need some like algebra stuff, right? So otherwise it's not going to be easy. Okay, so next one is going to be simple, right? So just use addition rule. So P of A union B, and this is part of B. Okay, so is P of A plus P of B minus probability of their intersection. Since they're independent, so this one is P of A plus P of B. Okay, so minus P of A times P of B. So equals what? Okay, so here is 1/2. All right, so 1/2 minus 1/2 times 1/2. So which equals what? 3/4. Okay, so 3/4. Okay, so very good. All right, so that's about this example, right? So you see that we use these conditional probabilities, right? And then use the property of independence. We can find out the probability about B and also the probability of A. Yes, so you need to know the properties of independence and also conditional probability to solve this question, right? And also some algebra, right? So yes, so that's about this question. And all right, so I think, okay. Okay, now let's move on to the independence of multiple events. All right, so let's consider the events A1, A2 till AN are said to be mutually independent. They are mutually independent if what? For any subset AI1, AI2, and AIK, k is less or equal to n, then the intersection, probability of the intersection equals the product of their probabilities. Right? This is for any subset, any selection of the events. Their probability of their intersection equals the probability, product of their probabilities. All right. So in particular, for three events A, B, C, right? So they're mutually inclusive, mutually independent mean if what? For any selection, right? So A intersect B, A intersect C, B intersect C, and also A intersect B and intersect C, right? So this equation all holds. Then we say they are mutually independent. Okay, so especially they have to hold for all equations. All these equations must hold simultaneously, right? Then we can say they are mutually independent. All right, so consider this example, right? Flip a fair coin 4 times and the sequence of heads and tails are recorded. And we want to find the probability that getting 4 heads. Okay, so even A, right? So now flip a fair coin, now we say that they're independent from trail to trail, yes? So getting 4 head is going to probability of head 1 intersect head 2, head 3, intersect head 4, right? So now because they're independent, we know that is H1, H2, H3, H4, right? So now which is what? 1/2 times 1/2 times 1/2 times 1/2, which is 1/16. Okay, so simple, right? So B, right? Find the probability of getting exactly 1 head. All right, so probability of exactly 1 head equals what? Now probably only the first one is a head. Intersect tail 2, right? Tail 3, tail 4, plus probability only the second one is a tail, is a head. 2, T 3, T4, and similarly, T1 intersect T2, intersect H3, intersect T4, and finally, the probability of T1 intersect T2, intersect T3, intersect H4, right? Now, since they are all independent, so it's going to be 1/2 times 1/2 times 1/2 times 1/2 plus, okay, similar, are they all 1/2 times 1/2 times 1/2 times 1/2 plus 1/2 times 1/2 times 1/2 times 1/2. Okay, so finally, 1/2 times 1/2 times 1/2 times 1/2. So you can see that this is what? 1/4. Yes, 1/4. Now, that's how we find this one, right? So because they're independent, right? So we can just use the probability of the intersection equals the product of their probabilities. So very, very good. Okay, now let's consider another one, right? So consider this example. Now consider rolling a 4-sided die. The sample space is 1 through 4, and A1 is 1, 2, A2 is 1, 3, and A3 is 1, 4. Given all outcomes are equally likely, show that these events are pairwise independent, right? So that is AI and J are independent for any I does not, but not mutually independent, all right? But not mutually independent. Okay, so let's consider firstly pairwise independent. Okay, so solution. Okay, so you can see that A1, for this A1 and A2, A1 intersect A2 is just 1, right? And A1 intersect A3 is also simply 1, right? So A2 intersect A3 again is 1, right? So it seems like we do have P of A1 intersect A2 equals P of 1, right? So which is what? 1/4. Now this 1/4 do equals P of A1 times P of A2, because what? A1 is 2 out of 4, A2 is 2 out of 4, right? So 1/2 times 1/2 is 1/4. So this means what? A1 and A2 are independent, right? So similarly, we can prove that the other, any pair, A1 and A3 are independent, and all right, so A2 and A3 are also independent, right? So we have, they are all then that's what that means, they are pairwise independent, right? So for any pair of events, they are independent, but not mutually independent. Okay, so what do we mean by mutually independent? So for 3 events mutually independent, so it has to be what? Not just the pairwise independent, right? But also the product of this equation must also holds, right? So all the equation holds. So now let's check the final equation, right? So if this equation holds for this example, so okay, sorry. So now it's going to be, what is the intersection of A1 intersect A2 intersect A3? Now you can see that it's just 1, right? So A1, A2, A3, right? The intersection is 1. So the probability of their intersection is going to be 1/4, right? Now, however, it's not equal to, right, P of A3 does not equal to this their product, right? Because this their product is what? Okay, you can see that's 1/2 times 1/2 times 1/2. That's 1/8, right? That's 1/8. So they're not equal, right? So they're not equal. Now, hence, they're not mutually independent, right? So not mutually independent. Okay, all right. So thank you for your attention. And okay, all right. So I think we are going to stop here for this video. And thank you very much for watching the video. And if you feel like this is helpful, please leave a comment and smash on the like button. If you think somebody else will be benefit from this video, please share this video to your friend. Thank you very much. I will see you in the next video. Bye bye.